First, I'd like to thank the organizer for giving me the opportunity to share some of the experience of our lab with the AllType FASTplex. So this is my disclosure slide. So actually, I divided my presentation to three objectives. So first, I'm going to touch base on the AllType FASTplex version 1, which we initially started our validation. And then I'm going to move into the AllType FASTplex version 2. And then I'll wrap up my presentation at the end by giving an alternative method for the version 2. So please keep tuned. So before implementation of our NGS, we used to do our HLA typing through depending on the category. So for solid organs, we used to do low resolution beads for HLA-A, B, C, DR, and 3, 4, 5. And then we use the high definition SSO beads for the DQ and the DP. For bone marrow transplant, we used to do SSO by using the XR beads for HLA-A, B, C, DR, and then SSO low resolution for 3, 4, 5. And SSO high definition for DQ and DP. So based on this typing method, this is how our report was looking like. You can see very nice high resolution typing at the top, but when you look at our disclaimer at the bottom of the report, you can see all the non-excluded alleles that we currently cannot resolve using this method. And with the implementation of the CIWD version 3, even with our current method, there was some other new alleles that has been in the new CIWD that we cannot resolve. And I highlighted this in yellow, as you can see in the presentation here. So this means that our method that we were using was become an outdated method, and we have to move on and carry on with NGS. So this is just the timeline of the when we started to implement the NGS. It took us 18 months from start to finish, but the actual validation only took 3 months. So if there is a new lab and they are thinking of implementing NGS and they want to implement it in the next 2 years, so this is the time when you have to start the negotiation with your institute. And the main you have to start also negotiation with your IT, because at the beginning I thought that IT is just one person, but then it became a committee and there was over 20 people from different IT departments, security, safety, certificates, storage, applications, like a lot. So, and you have to convince the 20 of them that your product is safe and secure for the patient health system. So we did the validation using 320 sample from our stored DNA bank, which is equivalent approximately to 640 alleles. And we did allele frequency, so to make sure that we cover 80% of the normal population. And as you can see here in the table, this is the discordant that we could find. We found comparing our older method to the NGS method. And you can see that our old method was just basically SSO and SSP, so we were lucky to get this only this number 5 alleles. So in this table, this is just some of the discordant that we find using the new method. So with AllType FASTplex, as an example, it was typed as 00201 and 00224. When we compared it to our reference method, it was actually 001 and 002. And then when we looked back into the SSO run, which was done 2 years ago, we found that this was actually a sample carryover in SSO, and we had to make a corrected report after 2 years. The next one is AllType FASTplex gave us an A0201 and 3101 null. Even using the SSP trays which can resolve this rare null alleles, we were not able to resolve it. And then when I contacted the vendor who supplied us with the SSP, they said, we just supplied the primer, but we cannot guarantee that it's going to work with every single rare allele. So even if the SSP tray saying that they can resolve this allele, they've never validated in their company, because there is this allele probably maybe have been seen once or twice. So it's very difficult to get a patient having this rare allele. The third example here was an example of an allele dropout, which is somehow common with any NGS. So when compared to the reference method has actually found a DR beta 01 and 04. And when we repeated the same sample again, we were able to rescue this allele dropout. And we found that the DNA quality that we initially used was not a very good quality. So it's important when you do an NGS is the quality of your DNA, because if you have a bad quality of DNA, then this is when you start to get some issues. The last example here was the DP2301. It was homozygous by FASTplex AllType. With our older method, it was heterozygous 0401 and 2301. And then when we went back to the string, we found that the actual 0401 was one of the rare allele. 0401, I think it was like 04168 or something like this. And then in the same string was the 2301, and the technologist just picked the first one and was reported as this. So we went and we did another corrective report. And then we said, we're going to stop now, otherwise we're going to start fixing all our reports. So the conclusion of objective one, that AllType FASTplex provided more than 99% concordance with our reference method, and MiniSeg provided a solution for small lab, size lab, HLA lab that is interested in NGS implementation in more economical, or if there is a tight budget. So with every limitation, with every technique there is some limitation. So the limitation in the version 1, that it didn't sequence Exon 1. And when you look at the alleles that are present in Exon 1 and for the Class 2, you can see there is a number of alleles. Most of these alleles are very rare alleles that you don't have to exclude. But DR beta 1210 is a common one. So most of the lab who are using this technique either can report it as a 1201P or a G group. The other limitation here is the version 1 used the dual index strategy, which is basically consists of two barcoding. You put your barcodes on either ends of your fragments, and it's the I7 and the I5. And I'm not sure it's just keeping moving by itself. So One Lambda usually supply the I7 barcoding in a form of 96 well, but only the first 3 wells, the 3 rows, columns are filled with the barcode, and this actually column are sufficient for 96 samples. And in order to make available for 96 samples, the I5 barcode is in a different format, which is in tubes, so you can mix between I5 and the universal barcode in order to cover the 96 unique barcoding. So, and this was not an issue for our lab, since our lab is more like a small to medium-sized lab, because we only do 24 samples per run. So we never used, we never have to use 4 different pooling. We only did the example on the right side here, which is just we do one pool. This will be maybe more with big size lab when they do 48 samples or 96, then they have to do 4 pools, and then after they do the 4 pools and they attach the barcoding, then they can pool them again back into one sample. So this comes to the objective 2, because One Lambda was listening to this recommendation, so they started to add in version 2 sequence of Exon 1. So this actually solved all these alleles that we cannot solve with Exon 1. And it comes as a supplementary primer, so you can just spike. It's the same technique as the other one. You just spike your primer, mix with it, and you can now sequence Exon 1 for class 2, DR, DQ, and DP. The other difference in version 2 now, and instead, and this is actually for the bigger lab, that you don't have to pool into 4 different tubes. Now you can pool them into one pool, because now they have a redesigned sample, an universal barcode that can have 96 unique library sampling. So in concordance, we tested this. I think this product just launched last week. So we didn't have enough to run, but we ran 24 sample, and we got, like, as you can see, 100% concordance when we compared it to version 1. We just noticed that comparing version 2 to version 1, the total reads, we noticed that the total number of reads on the DR and the DQ and the DP locus was significantly higher in version 2. So I'm assuming this is because of the addition of Exon 1. And then when we looked at the length of the read, the length of the read was mostly the same. Depth of the read was mostly the same between most of the loci except the DQ. And then when you look at the specifically in Exon 1 DQ, I haven't seen this number before. We have got a depth of read of 5500x. So when you look at the like the histogram, so what you see here, what you see in purple, this is the exon. So the first exon is Exon 1, and then Exon 2, 3, and 4, and 6. And you can see that the number of reads in Exon 1 is significantly higher than the rest of the exon. So it just gives you an uniformity reads, but at the end it doesn't affect your code, because although you have 5,500 depth in Exon 1, but you still have from 300 to 1,400 depths in the rest of the exons. So the conclusion of Objective 2 that the FASTplex version 2 provided 100% concordance comparing it to version 1. It solved the Exon 1 ambiguity in HLA-Class II, and now it's the issue for big labs. Now you can pool the sample only into one, using only one single tube. So this brings into the Objective 3, which is using the version 2 but do some modification. And this was done in collaboration with One Lambda. It was one of the feedback that we wanted to reduce the hands-on time. And One Lambda actually recommended to us to use this alternative protocol, and we were one of the labs that did this beta testing. So this is actually the normal protocol that we use in our lab, and this is not the recommended timeline of One Lambda, but this is the timeline that fits our staff and fits the workflow. So in day 1, usually we start in the afternoon by the long-range PCR, leave it overnight, and then the next day we do the purification, and then the quantification, then the diluting, barcoding, and then pooling, and then we stop here in day 2, and then take it to day 3, which is quantification and then sequencing. And the reason, although like One Lambda used to recommend that we can do it in one day, we found by the end of the day our technologies get exhausted, and the last step has a lot of calculations, so we decided just to move it to the next day, extra 2 hours, but you can guarantee a better result. And then in day 4, you do the analysis on the TSV, and then interfacing it with HistoTrack, and then by day 5, you can start reporting. So it's a 5 days turnaround time. So Using the alternative protocol is based on recommendation of One Lambda that this purification step can be omitted. So we actually tested this and we were able to omit this purification step. So by omitting this purification step, we were able to combine day 2 and day 3 into one day, because in the purification step you need to prepare your ethanol, you need to equilibrate your magnets, you need to, everything have to be room temperature, which takes some time during the beginning of the day, although it's not hands-on time, but the tech has to wait until all the reagent is reached the room temperature. So when we eliminated this step, the technologists can just take the plate and then just quantify it directly and then start on going on to the rest of the day. So by using this alternative method, we were able to reduce the turnaround time into only 4 days. But One Lambda recommended, in order to use this, you need a very high quality DNA. And you know, I usually like to challenge One Lambda, so I sneaked one of the buccal swab. As you can see here, this is actually a tape station. If you're not familiar with this one, it's like running your DNA on a gel, but it's more like a microchip. So you can see here sample number 6 has a little bit faint band, and this was a buccal swab. And usually a good genomic DNA would have a big chunk of DNA at a very high molecular weight, above 60 kb. And if you can see the last 2 samples, there is a little bit of smear because there is some degradation, but still most of the samples are in above the 60. And then what we did is we compared the 2 assays, which is the purified and the non-purified, and then the product or the amplicon, we run them again onto a tap station. So this is actually the tap station after the amplification of the purified, which is the recommended method. And you can see here, now you have 4 bands. So the top band represents your main amplicon. The 3 small bands is the Exon 1, amplification for DR, DQ, and DP, because this is the version 2. And then the lower band here, which is very faint, is the primer dimer, which same as what you see when you run an SSP gel. And then when we use the alternative protocol, which is the unpurified protocol, we still can get the same trend. You can still get the higher band in the 3 bands. But if you look at the bottom, you can see a big chunk of primer dimer because we didn't purify it. So this primer dimer is going to carry on with your experiment. But when we did the concordance, actually it gave us a very excellent result. We got 100% concordance between the version 1 using the recommended method and using the alternative method. We just noticed 3 samples out of the 24, which I highlighted here, has slightly higher background. Like for example, the first one, the A25, there is 20% of your reads were just noise or background. But if you look at the majority of the code, which is almost 80%, you have 542 depth. So it's sufficient to give you confidence that the C is the right code. And the same scenario for with the DQ alpha A1. The last example here, it was a split. So it was not just a high background, but when it reached the 50-50, then the software considered this as a novel allele. But because the number of reads is only, I think, like 22 and 21, so we know that this is not a novel allele, and this just needs to be repeated. The other thing we notice with this alternative method is that Exon 6 usually have less number of reads. But when we use this alternative method, it has more or less of reads, and then it results in one of the ambiguity that we used. We have seen it in most of the sample when it's tied by DQ beta 03, which is, it just cannot resolve the 03454, which is a very rare alleles. So, in conclusion of this objective 3, AllType FASTplex version 2 alternative method provided 100% concordance with the recommended protocol. It's a very promising tool to reduce hands-on time, but still some work is needed to complete it and to become clinically validated. At the end, I'd like to acknowledge the HIL lab staff and especially Destiny Webster. So she's the second from the right who did all this work, and I'm here only just to present it. And also I would like to thank One Lambda for giving us this opportunity, and I'll be happy to answer questions.